We want to talk about how we could have used a unit vector to find the vector force F when we stretched a rubber band from one point to another. Given that the displacement vector between one end of the rubber band and the other was the vector 9 centimeters, 10 centimeters. Now we figured that that had magnitude 13.5 centimeters at 48 degrees approximately, but we're not going to use those calculations. Now we are going to use the 13.5 centimeters that we get from the Pythagorean theorem. Magnitude of this vector is 13.5 centimeters. We're not going to use the angle. We don't need to, it turns out. And we'll see why, and we'll see how, just by using what we call a unit vector. And we've just seen unit vectors. Okay, well, the fact that this vector is 13.5 centimeters long means that we can measure the force or determine the force exerted by that rubber band when it has a length of 13.5 centimeters. And we asserted that that force was 12 newtons. Now, the question is, what is the vector force? Now, vector force has a magnitude and a direction. Well, if we know that this angle is 48 degrees, then since the direction of the force is the same as the direction of the displacement vector along the rubber band, we know that we have 12 newtons at 48 degrees. Well, that's how we did it previously. But we're going to not do that. We're not going to bother finding the 48 degrees. It isn't necessary. Okay, so how are we going to do this? Well, if we take the vector A and divide by its magnitude, now implicitly, if we multiply a vector by a number, it doesn't change by a positive number, it doesn't change its direction. It gets longer or shorter. If we multiply it by 2, it gets twice as long. If we multiply it by 1/3, it gets 1/3 as long. If we multiply it by negative, it changes direction to the opposite direction. But now what we're doing is we're multiplying essentially A by the reciprocal of A, or if you wish, dividing A by the magnitude of A. Magnitude of A is 13.5 centimeters. So we're going to make this vector 13.5 times shorter than it is. And that's easy to calculate. A is the vector 9 centimeters, 10 centimeters. And we're dividing then by 13.5 centimeters. Okay? Now, when we do that, two things. Well, we're going to divide the 9 centimeters by 13.5 centimeters. I believe that's going to give us 0.67. And then we're going to divide it, the 10 centimeters by 13.5 centimeters, giving us 0.7475, something like that. Okay? And I'll actually go ahead and use something to calculate those more accurately. 9 is 2/3 of this. But 10 is a little greater than that, and a little more than 10 over 14. So I'm thinking 0.74, 0.75, somewhere around there. Okay, well, the point then is when I divide this by this, if I divided this by 13.5, this vector would get 13.5 times shorter. Now, I'm dividing it, though, by 13.5 centimeters, so the result is going to be unitless. It's not going to be in centimeters anymore. So it's not, this is measured in a scale of centimeters. The unit vector is going to be measured in any scale that we choose to draw it. Can be drawn to any scale since we're no longer confined to the centimeters. Well, anyhow, if we divide this, we're going to get, I'm going to pause and check my figures. I'm saying, 2/3, 0.66, repeating, 0.67, and 0.75. Okay. Well, calculate this. I get 0.67, 0.74 to the nearest hundredth. And if these, if this is all calculated with the 13.5, it comes out very much as it should. Now, the magnitude of A divided by the magnitude of A is, of course, then the magnitude of the vector 0.67, 0.74, which is the square root of 0.67 squared plus 0.74 squared, and that's approximately 1. Now it's off a little bit because this 13.5 was rounded, and the 0.67 and 74 were rounded. 6.7 is really 0.66 repeating. 7.4 is pretty close to the 7.4. I believe this probably comes out between 0.99 and 1, and probably closer to 1 with the round-offs that I've used here. Okay, well, anyhow, the point is then that A over the magnitude of A is a unit vector, which is a vector of magnitude 1. No units. So let's include the word unitless here. Okay, well, but it has the direction of the vector A. Getting sloppy here. Okay. It's in the direction of A. Now let me draw a couple of things. Okay, I've sketched a vector here. I could sketch any length I want because remember, this A vector is in centimeters. This vector is unitless. Centimeters and unitless don't have the same measurement. Okay, if we just divided A by 13.5, then the vector would have a length of 1 centimeter. It would be, 1 over 13.5, be 13.5 times shorter than A. This is longer than that because I'm not drawing the vector A over 13.5. I'm drawing the unit vector A over 13.5 centimeters. Okay, well, anyhow, that's a unit vector in the direction of A. Now, if I multiply that vector by 12 newtons, then I'm going to have a vector whose magnitude is 12 newtons times the magnitude of the unit vector, which is 12 newtons times 1, which is just 12 newtons. It's going to have magnitude 12 newtons, and it's still going to be in the same direction since 12 newtons is a positive quantity. Okay, so I'm going to let U stand for the vector A over the magnitude of A, just to remind us that it's a unit vector, and we're going to remember by this definition that it's in the direction of the vector A. So when I multiply 12 newtons by the unit vector, I get 12 newtons times 0.6774 vector, our unit vector, and that's approximately then 8 newtons, 8.9 newtons. Okay, this vector has to have a magnitude that's 12 newtons times the magnitude of this vector. This magnitude of this vector, being a unit vector, is 1. So 12 newtons multiplied by this vector has to have magnitude 12 newtons times 1, which is, of course, just 12 newtons. So this is a vector of magnitude 12 newtons, and it is in the direction of A. Now, if we recall, some previous results in this series, that's exactly the vector that we got. I'll also note that if I multiply 0.74 by 12, I believe I actually get something. No, it rounds off to 8.9 newtons. Okay. It's pretty close to 8, rounding off to 8.8. It's between 8.8 and 8.9, but it turns out it is close to 8.9. Okay. So I can draw that vector on this sketch. Now this vector is in newtons. This unit vector was unitless, and this A vector was in centimeters. So the relative lengths of these vectors as we draw them are completely arbitrary since they're measured in completely different units. We don't know how big to make a newton. We don't know how big to make a centimeter, and we don't know how big to make something that's got magnitude just 1 with no units. So we can make them of any length. So in this case, I'm going to draw my 12 Newton vector. It's in the same direction as A. And of course, this is our force vector. Now this was our F12 vector, and that's equal to 8.0 newtons, 8.9 newtons, the same thing we calculated previously by multiplying 12 newtons times the sine of 48 degrees to get the 8.9 newtons, and by the cosine of 48 degrees to get the 8.0 newtons. But now we didn't calculate it that way. We calculated it instead by calculating this unit vector and multiplying this unit vector by 12 newtons. And that's a very important and very powerful technique.